And looking at the treatment, I'm able to partition them into what we call control group and the experimental group, and a situation where the experimental group can also be further partitioned. In that situation, we can actually compare, okay, the experimental group and the control group, okay, and putting into consideration one unit of measurement. But in a situation where the variable of interest is more than one, and we actually want to compare across groups, what are we going to do? Okay, so I want to tell you that we have multivariate version. Okay, we got multivariate version, and that's exactly what we're going to be doing today, that we call multivariate analysis of variance. Okay, so in the in the univariate setting, we got a lot of tests that we normally carried out, like when we used to talk about a paired match comparison of two treatments. Okay, we did that in univariate setting. So how can we achieve something like this as well in multivariate setting? Okay, so we're going to focus on that today. Then we also have what we call repeated measures within subjects across treatments. Some of you have heard about randomized block design in the analysis of experiments. Okay, so today we're actually going to be focusing on the multivariate, uh, you know, generalization, okay, of the univariate. Okay, so we're also going to look at comparing two treatment population within independent samples. Then we're going to look at one-way analysis of variance. We're going to look at testing the quality of variance covariance matrices. We're going to look at two-way analysis of variance and so on like that. Okay. Now, I want to start with the paired comparisons. Before I move forward, can you guys hear me clearly?
Yes.
Thank you so much. I just want to confirm that. Okay, so in univariate analysis, there's what we call paired comparisons. Okay, uh, what do we mean by paired comparison? In a situation where I actually want to compare uh, the situations of things before intervention with after intervention. Okay, so something that has to do with before and after. But this time around, a single variable is involved. When a single variable is involved, of course, we're talking about univariate. Okay, now I want to start from the univariate perspective for the paired comparisons. Okay, now uh, we have, this is just the difference between before and after. Okay, and the DJ here is talking about the difference. Okay, uh, maybe in our place of work, uh, maybe the company officials or management are trying to put some measures in place, probably to boost uh, the morale of workers, okay, so that the workers will be able to become more committed to their work, okay. So maybe what the management put in place is just that maybe they increase uh, the wages, okay. Now, do you know that we can actually have a way to compare the wages of workers the performance of workers before the salary was increased and after the salary was increased, provided that we still have the same set of workers. Okay. For instance, if I happens to be working in that company, they can actually measure my average performance before my salary was increased and after it was increased. Okay. So that is why what I have here is just like the difference between before and after. Okay. But you know what? Uh, in a situation, so which means I got it in this way because I got two set of variables this time around. It look like having two set of variables. Okay. Because a variable we're actually going to represent before, and the other one is actually going to represent after. Okay. So I'm going to have it this way. Okay. In a vector form, and it's actually going to follow a normal distribution. Okay. And the distribution, of course, is identically normally distributed, the two variables right here. And you know what? They're actually going to have their mean vector, the mu1 and the mu2. The mu1 right here is just the mean of this, and the mu2 is just the mean of that. Okay? Of course, this is going to be the variance covariance. Okay? I'm actually going to have variance covariance because I got two variables. If I have one variable, I'm only going to be talking about variance. But when you have two variables, of course, you're actually going to have variance covariance. So this guy here is going to be the variance of the first variable, and this is going to be the variance of the second variable. And what I have here actually going to be variance covariance. Okay? So I think you can see that right now. So, and that actually implies that DJ is normally distributed with, the data equal mu1 minus mu2, because what we're doing right here is that the difference between the variable before and after. Right here, we're looking at the difference between the means of the variable before and after. Okay? And what I have here is actually going to be the variance of the difference. Okay? The variance of the difference. Okay? So this is the variance of the difference. Of course, you know where to get the sigma 11 is right here. And sigma 22 is actually here. Okay? And of course, you can figure out the sigma 22, which is right here. And this guy here is part of this. Okay? Now, do you know that we can actually find the mean of the difference? Okay? What I mean by that is that, okay, if I want to, if some set of individuals actually want to reduce their weight and they are trying to dieting, okay? They're trying to dieting in a way to reduce their weight. Okay? We can actually look, investigate we can compare the weights of this patient, of these people before dieting, okay? And then after dieting, we can compare the two. And a way to compare, mathematically, you're actually going to subtract, okay? Just like you're subtracting my weight before dieting, okay? And subtract from after dieting, my weight after dieting, okay? So, of course, when I do that, it's not going to be only me, okay? You have a lot of individuals that you actually find the difference, okay? Therefore, difference now becomes a random variable that you can actually find the mean, okay? So the formula here is that, okay, trying to find the mean, okay? And right here, you can also find the variance. So you are actually finding the variance of the difference right here. Okay. And if I want to test an hypothesis about the value of the mean of the difference, what I have here is the mean of the difference. Maybe I want to test that the mean of the difference is equal to an hypothesized value. And the hypothesized value is theta. Okay. The hypothesized value here is theta. Okay. And you know, of course, the theta is actually going to be the difference between the true mean difference. Okay. So if I want to do that, of course, this is going to be the test statistic that I'm actually going to use. And the distribution of the test will follow a t distribution with n minus 1 degree of freedom. Okay. So this is what we do in the univariate case. Okay. So which means if I take a sample of measurement, okay, if I take a sample of measurement where I have, you know, two sets of variables. Don't forget the first variable is actually going to be before, and the second set of variable is actually going to be after. Okay, and you know what? The number of units here should be the number of units here because they have to be matched. They have to be paired. I'm actually using the same set of individuals. Okay, so this DJ for Sji to be equal to Sj2, it means there is no difference between before and after. Okay? If there is no difference between before and after, it means the difference between them is 0. So what I'm actually going to be testing under the hypothesis is actually going to be theta equal to 0. Okay? Theta equal to 0 actually means that there is no difference between before intervention and after intervention. And why the alternative actually indicating that there's a difference. Okay. And of course, if I want to do that, I'm actually going to use this as a test statistic. Okay. Where this is going to be the mean of the difference. Okay. This is going to be the hypothesized value because the hypothesized value is going to be equal to 0. Okay. And of course, this is going to be the standard deviation of the difference. Okay. And what I have right here, it's actually going to be the sample size. Okay. And what I have here is going to be the critical value. I'm actually going to check this from the table. Okay. So that if the calculated here is greater than the value that I check from the table, I'm actually going to reject the non-hypothesis. Okay. And this is the way to figure out the p-value. If I want to take a decision using the p-value, of course, this is what I'm going to compute. Okay. And of course, if the p-value is less than a given level of significance, I'm actually going to reject the non-hypothesis. Okay. So I'm actually trying to tell you we got several ways to take decision regarding the non-hypothesis. Okay. If you take a look at here, if this guy here, if what I calculate here, that is the test statistic value, if it is greater than this value, I'm actually going to reject. And that is why R means rejection region. Okay. Or I compute my p-value and I compare my p-value with the level of significance. And if the p-value is less than, you know, a given level of significance, and I'm actually going to reject. Okay. And you know what? I can also do 1 minus alpha 100% confidence interval for data. Okay. I can do confidence interval for data. And if I want to do that, okay, it's going to be the d bar plus or minus, you know, the critical value that I mentioned right here. Okay. Then the standard deviation divided by square root of n. So all what I'm doing here, I'm still talking about univariate. Okay. So this is what you've done before. Okay. I started from the univariate just for you to be able to understand by the time I'm dealing with the multivariate. Okay. So now from this now, can we have a situation? Can we now have can we now generalize that to a situation where the number of variables involved, okay, is more than one, okay? Now, the one we did before in the univariate, we have just one variable that was partitioned into before and after, okay? You see one major variable, only that one major variable was partitioned into before and after, okay? Now, what if in a situation where I have more than one variable, okay? If I have more than one variable that I also want to partition into before and after, and that is multivariate, okay? So, in generalizing that right now, it means I'm actually going to have the, a vector of difference, okay? Before I only have one difference, okay? I only have one difference, right? I'm going to take you back to the univariate. You're going to see what I'm talking about. Can you see that now? I only have the one difference here. This is scalar. But in a multivariate case, the difference is actually going to be a vector because I'm actually going to have more than one difference, okay? So take a look at this right now, and that is why I'm actually going to have a vector of difference. Look at that, okay? The first one here, before and after. I'm also going to have another before and after, okay? So maybe the difference here is, maybe I'm talking about, let me see, weight, blood pressure, okay? I'm talking about more than one variable at a time, okay? Maybe I want to reduce my BP, okay? Now, if I want to reduce my BP, okay, and then in the process of doing that, maybe I'm being placed on a drug, okay? If I'm being placed on a drug, then the first difference here may be the difference between my blood pressure before and after, okay? Maybe the difference between my blood pressure before and after. Then the second difference may be the difference between my weight before and after. Maybe I also want to reduce my weight. I also want to reduce my BP. I want to reduce my weight, okay? So I'm just trying to tell you we're going to have a lot of difference. The difference is now going to be a vector, okay? And when a difference is a vector, then we can actually talk about the mean of that. And that's exactly what we have here. We can talk about the variance of that. Of course, if you want to talk about the variance of that, because it's a vector, it's actually going to be a variance covariance, okay? It's actually going to be a variance covariance. And we can actually find the mean of a particular difference. We can find the mean of each of these differences using the formula right here, okay? And we can actually find the variance of each of the difference. We can, and as well as the covariance of each of the difference. And that's exactly what we're doing right here, okay? And then the idea of so when you find this one here now, and this is a way to find, to express that, okay? And you know what? I can actually now say I got a vector of a difference that actually follow a normal distribution with the mean vector this and the variance covariance this, okay? For your information, the DJ here is a vector mean that we define right here. Can you see that now? It's a vector mean that we define right here. And that is the reason why the distribution, it follows a normal distribution. This guy here is also a mean vector, okay, which is right here. And this guy here, of course, is the variance covariance of this, because this is a vector, okay? Now, the idea of the Hotelin T squared can now be applied. The idea of Hotelin T squared can now be applied. Okay, now look at the formula right now for the Hotelin T squared, okay? And for your information, the D bar right here, okay, the D bar right here, we actually going to be the sample mean of the difference. And the sample mean of the difference is actually going to be a vector. Okay, and the data right here is actually going to be a vector mean, particularly maybe an hypothesized one. Okay, and what I have right here is a variance, the inverse of the variance covariance. Okay, and of course we are also going to have this, we're going to be taking this one from the idea of the Ottolenghi square, and this guy here follows an F distribution. Okay, so if n and n minus p are both large, then the t squared actually follow chi-square distribution regardless of the distribution of the differences. Okay, so when I have a sample data now, where I get different kind of differences, okay, where I get different kind of differences, okay, this is a vector. Okay, I can find the mean of each of the differences. Okay, and I can as well, find the variance and the covariance. I can as well find the t squared. Okay, and if I want to test an hypothesis, or you know what, the hypothesis that I'm actually testing right here is that the vector of differences is equal to 0. So the hypothesis that I'm testing right here is different from the hypothesis that I'm testing under the univariate case. Under the univariate case, I'm only having a single difference. Okay? I'm only having a single difference. Okay? So, but in the multivariate case, I'm actually going to have the vector of differences. Okay, so this is actually representing the vector of differences. Okay, so this is the test statistic that we're actually going to use. And don't forget that the t squared here is this. Look at that. You need to first compute this. When you compute this one, then you're going to put the t squared here to multiply this guy here. And this is going to be the test statistic for the test. So if this is the test statistic for the test, this is going to be the rejection region. And this is what I'm actually going to use to figure out the p-value that I can actually be used to take decision. Okay. Now, from there, we can also have the confidence interval on the vector means of the difference. Okay, so this is how to do the confidence interval. And you remember the other time I walk you through different kind of confidence interval in multivariate setting. We're also going to have that here. Okay, so this is the formula right here is 1 minus alpha 100% confidence interval for the vector of the pair of the differences. Okay, so can you see that now? And what I have here is more or less like one at a time that I talked about the other time, one at a time. Okay, and what I have here is the Bonferroni that we talked about the other time, the Bonferroni. Okay, so I think you can see that right now. Okay, before I move to the repeated measures for comparing Q treatment within subject, is there anyone who need clarification on what I just delivered right now? Can you guys hear me?
Yes.
Okay, so I actually want to know if there is anyone who actually need more clarification on what I just explained right now concerning peer comparison in multivariate case. Okay, silence actually implies that you guys are good. So I'm actually going to go into repeated measures for comparing Q treatments within subjects. Now, Let me ask you this question. How many of you have done analysis of variance before? How many of you? Is there anyone who have done analysis of variance before?
Yes.
Okay, thanks for sharing. Have you also heard about two-way ANOVA? Have you
Yes.
guys heard about two-way ANOVA? Has anyone asked about two-way ANOVA?
Yes.
Okay. Now, in two-way analysis of variance, we have one-way analysis of variance, we have two-way analysis of variance, three-way analysis of variance, and so on like that. Okay. Now, what I want to talk about right here, when you have a randomized complete block design, okay, the randomized complete block design is just like, I want to, it's more or less like a two-way analysis of variance, because I'm actually going to be testing the effect of treatment. I'm also going to be testing for the effect of block. Let me tell you this. Let me give you a typical example of a randomized complete block design in univariate setting, for you to be able to understand what I want to teach right now for the multivariate. Okay. If I'm compare 3 levels of fertilizers on the yield of crops, let's assume that I want to compare 3 varieties of fertilizer. The fertilizer that I'm talking about, or maybe I'm actually talking about, um, let me just, okay, maybe I'm talking about one level, A level of fertilizer, B level of fertilizer, C level of fertilizer, and D level of fertilizer. Okay. Now, it's the same level of it's the same fertilizer. Okay, but at different levels. What do I mean by different levels? Maybe I want to consider a 0 kilogram of fertilizer. A 0 kilogram is more or less like, okay, I don't want to apply that. That is more or less like a control. Okay, so maybe I'm trying to grow maize. Okay, I'm trying to grow corn in my farm. Okay, and I want to test a situation where I don't apply fertilizer at all, because that is going to be 0 kilogram. Okay, if I take 5 kilogram, okay, or and I also take 10 kilogram, and I take 15 kilogram. I think what I'm going to do right now, I'm going to have a new share, so that you will be able to understand what I'm talking about. Can you guys see my whiteboard right now? Can you guys see my board?
I can't. Oh, okay. I can see it now.
Oh, you can see it now. Okay. Now, in the process, uh, of comparing, okay, levels of fertilizers. Okay. Now, let's assume that the treatment that we want to consider, one, it has level A, and level A is 0 kilogram. Of course, the 0 kilogram is more or less like control. Okay. Now, why do I want to, in the process of comparing levels of fertilizer, in the growth of corn. Have you guys heard about corn, right? I think you guys know corn, right? I just want the one they also call maize. Some countries call it maize. Okay. I think you guys know about corn, right?
Yeah.
Okay. I just want to be sure. They also call it maize. Okay. So maybe I have the first level of my treatment is that, and the second one, maybe I apply 5 kilogram of fertilizer. The third one, maybe I apply 10 kilogram. Okay. The third one, maybe I apply 15 kilogram. Okay. Now, what I have right here, okay, if I only focus on this alone, okay, if I want to use, if what I want to use, if I apply, if I have a farmland where I want to apply this, okay, if any pot, any let me see, if any experimental unit, can receive any treatment, okay, can receive any treatment, then then we are interested, we're interested in doing one-way analysis of variance. Okay, one-way analysis of variance. Okay, so we're doing one-way analysis of variance if, of course, I want to apply these fertilizers, these levels of fertilizer on my farmland. Okay, I want to apply that on my farmland, and if any of the experimental unit, that is the plots. Okay, when I say experimental unit, I'm actually referring to the plots. Okay, if any of the plots can receive any of this, of course, I'm actually using one-way analysis of variance. Okay, but in a situation, give me 1 second so that you guys can be able to see. Okay, let me make that one to go up. Okay, so but in a situation where if we have heterogeneous, farmland. What do I mean by heterogeneous farmland? In my farmland, okay, if plots are heterogeneous in nature, okay, so what I'm going to do, I need to partition. I need to partition the experimental plot. I need to partition the experimental plot, okay, into homogeneous units. Okay. Now, I partition them into homogeneous units means that, okay, it's like grouping them. Okay, so that in this area I know what to do. I know what to plot. This area I know. So in one area I'm going to plot, I'm going to apply these levels of fertilizer. In another area I'm going to apply. So which means I'm introducing what we call blocking. Okay. So here, blocking restriction, okay, is being introduced. Okay, here blocking restriction is being introduced. And if a blocking restriction is being introduced, of course, your model is actually going to change from one way or another. What you're going to have right here now is going to be what we call the randomized complete block design. Okay? Because you're actually going to be testing for the effect of treatment. Not only that, you are also going to be testing for the effect of blocks. Okay? But you know what? This is what we do in the univariate setting. So in the univariate setting, the fact remains that the fertilizer here is the same, but only that we have different levels. Okay? It's the same fertilizer, but only that we're considering it at different levels. But what if in a situation where we have two different fertilizers? Two different. Okay? What if in a situation where we have two different fertilizer, one has levels like this and the other one has levels as well? And in that situation, we are also introducing blocking. Okay? Then we're talking about multivariate. Okay? I think you now understand the difference between the univariate randomized block design and the multivariate randomized block design. Okay? And that's exactly what I actually want to showcase right here. So I'm going to go back to my slide right now. So that is exactly what we are trying, to do. Okay, so take a look at what I have here right now. I got an X, okay? I got a set of variables. It could be set of treatments where each of them, they get their levels, okay? Of course, we can find the mean of that. We can find the variance of the vector, which is going to be variance covariance. And we can actually use the formula here to find the mean of each of that, okay? And you know what? Yesterday, as I talked about sampling distribution of multivariate, we can do the expected value of the mean, which is going to be this. And of course, the variance of the mean, don't forget, it's going to be this divided by n. You remember what we did in sampling distribution in multivariate setting, okay? And if I want to talk about contrast, where I will be able to compare one treatment from the other, well, that's what we're going to do. Of course, we can do mu1 minus mu2, mu1 minus mu3. Of course, this is what we call contrast. It's more or less like a pairwise comparison. Okay? Pairwise comparison. Okay? The M that is here is like I get a lot of stuff in the middle. Okay? This is going to be the last one. So this is a pairwise comparison. So what is the meaning of what I have right here? So this is trying to tell me, okay, I'm only focusing on the first and the second treatment. Though I know I got a lot of treatments, I got Q number of treatments, but I can only compare two at a time. Okay, so if I compare treatment 1 and 2, then 1, the coefficient of this is going to be 1, the coefficient of this is going to be minus 1, then the 0 for others. Okay, this is mu1 and mu3, mu1 minus mu3. So mu1 is going to have 1, mu3 is going to have minus 1. Every other one is actually going to be 0. Okay. Now, I think you can see that now. Okay. And this is the whole of what I have here is more or less having a linear combination. Okay. So this is when you want to consider a mu2 minus mu1. So it's more or less what we're trying to do right here. Okay. And you know what? If I want to test equality of means, the equality of mean that I'm testing is more or less testing for the linear combination of one equal to the linear combination of the other one. Now take a look at what I'm doing right here. When you look at this is the same thing as this, because we can actually split this to be a constant, to be this and this guy here. Okay, because when I use this to multiply, this is what I'm going to have. So this is what we call the C1 mu. When I do mu2 minus mu1 and stuff like that, I'm actually going to have this. So this equal to this is more or less testing that, all the means are equal. Okay? And that's exactly what we have here. Okay? And you know what? We can find the expected value of that. We can find the variance of that. So these are just theoretical development. I'm actually going to walk you through how you can apply that. So, and this is the repeated measure. If you want to have, if you have for observed measurement, this is what you're going to have. So this is what we are testing, and this is the test statistic. Okay, if this is the test statistic, what is my t squared? This is my t squared right here. Okay, this is my t squared right here. Okay, so what is my x bar? Of course, this is your x bar. Of course, it's going to be the mean vector. Okay, vector mean. Okay, and of course, you're going to have your c. And you know what? Your c right here is here. I think you can see that now. The matrix here is your c. This is like c2 here. This is your c1 here. Okay. And you know what? This is a, if this guy here is greater than f, this is the rejection region. You're going to reject this hypothesis. And this is the p-value. And also, we also have a simultaneous confidence interval for that. Okay. This is a simultaneous confidence interval for that. Okay. I believe you're going to understand more when we are applying. But you need, what I'm trying to show you now is just for you to know the theoretical development and for you to be able to know the right formula you're actually going to use when you are given question in multivariate. Okay. So for situation where you want to compare two population treatment, okay, and they are independent samples. This is the independent sample. If you look at the one we did before, we the period, that was not independent, that was dependent, because we're using the same set of individuals, okay, before and after that I talk about. But this is an independent, for independent sample. How do we go about it? Okay, so this is for sample. It means I'm going to have set of sample 1 and I'm going to have set of sample 2. Okay, maybe this set of sample 1, maybe these are the economic variables in a particular country, and this is economic variables in another country. Okay, so this may be exchange rate, inflation rate, consumer price index, and so on for one particular country, and this may be for others, for another country. Maybe you want to compare. Okay, so right here, okay, we're actually going to have the mean of that, the mean vector. We're going to have the variance covariance, and of course, this is how you can use to figure out the mean of each of the variable in this first sample. And this is what you're going to use to figure out the variance and the variance, the variance and the covariance. This is what you're going to use to set up your variance covariance matrix for this particular sample of vectors. Okay, you're also going to do the same thing right here. Can you see that now? And you know what? What do you want to test? You actually want to compare. What are you comparing? You're comparing this guy here with this guy here. Look at that. That's how we're comparing. Okay? I'm going to say that again. You are actually comparing, the vector of x6 here with the vector of x6 here. It's like comparing the economic variables of one country with another country, or comparing the variables, the measurement of maybe some patient has COVID-19. Okay, maybe this group now they got COVID-19. These are their variables. Maybe the blood pressure, the weight, the height, and so on like that. Okay, so maybe you collected this from one country. Okay, maybe for instance you collected this from United States. Okay, of some set of individuals. But the second sample, maybe you collect it from somewhere else. Okay. Okay. Now you now want to compare. Okay. When you are comparing, want to compare the major vector. Okay. And if you want to compare, let me tell you, one way to compare this, you can actually compare the mean vector, and you can also compare the variance covariance. Okay. You can compare the mu1. The mu1 here is more or less like the vector mean of this. The mu2 is the vector mean of that. I can compare this with this. We can also compare this is the variance covariance of this set of variables right here. And this is the variance covariance of this set of variables right here. And that is the reason why, if you look at what I have right here, I'm actually going to say Sij. When I say Xij, I mean the set of variable here, and the set of variable here actually follows a normal distribution with this mu and this. So if my j equal to 1, if my j equal to 1, I'm referring to this guy here. I'm referring to the set of variables here. Okay, and if it is equal to 1, I'm actually going to have mu1, which is going to be this vector mean, and the variance covariance, look at that, it's going to be 1. Okay, and if j equal to 2, I'm actually talking about this particular guy here, and it has a mean of mu2, which is going to be vector mean, is actually going to be here, and this as a variance covariance. Okay, so you know what? I can actually test if the variance covariance of this set of variable equal to the variance covariance of this set of variable. That's exactly what we're talking about right here. Okay, so if we have the assumption that the variance covariance here equal to the variance covariance here, then we can actually pull the variance covariance, just similar to the way we pull variances in univariate setting. I quickly want to remind you of the formula. The formula we normally use in the univariate setting is this, if you want to pull variance. Can somebody confirm if you guys have seen this formula before, for those of you who have done lower statistics course? Have you seen that before?
I don't remember I seen it before.
Oh, you don't remember that? Okay, so this is a formula. This is what we call pooled. We use this formula to pool variance in a situation where we are testing for equality of means in two populations, and when we have the assumption that the population variances are the same, the fact that population variances are the same does not indicate that population standard deviation are the same. I mean, does not indicate that the sample variances are the same. Okay, so we use this idea to pull the variance. Okay, so what I have here is what we use in the univariate setting. If I want to, you know, try to extend that to multivariate, okay, this is what I'm actually going to have. Okay, I'm actually going to have this formula right here. Okay, so which means, you don't need to care about what I'm doing right here. What you need to care about is a final formula. Okay, so it means my pool variance now is this guy here. Okay, so 1 over n plus 1 plus 1 over n, 1 over n1 plus 1 over n2 variance covariance. So which means I more or less have a pool. Okay, so look at that. So that is the formula we have. So if I want to test an hypothesis now about the difference of the two populations, what am I testing right here? I'm actually testing the mean vector of a group. I'm comparing with the mean vector of another group, just like what I'm talking about right here, about having two set of groups. I'm going to show you right here. Yeah, I told you the other time that maybe these are a set of variables that we collected in a country for those who have COVID-19, okay? And this is for another country. So right now, we want to test for the equality of the mean, okay? Equality of the mean vector is just that is the weight of somebody, or is the temperature if this represents temperature here, this is also going to represent temperature here. Is the temperature of somebody who tested for COVID-19 positive for COVID-19 in the United States the same as that of somebody who tested for COVID-19 in Canada? Okay, and just like that. So we are trying to compare the mean vector, and that's exactly what we're trying to test right here. I'm going to show you now. So right here, we're trying to say there is no difference between the mean vector. Okay, and this is trying to say there's a difference. And what I have right here is a formula that I'm actually going to use as my test statistic. And the question remains, what is going to be my t-squared? My t-squared is this. Okay, you need to worry about this formula and look at this formula. This guy here is going to be the sample mean vector, the difference of the sample mean vector. Okay, this is going to be the hypothesized value of the vector mean. Okay, so of course this is going to be the number of sample taken from each country. This is the number of sample of the other country, and this is going to be the pool. Okay, how am I going to get the S pool here? The S pool here is what I'm actually showing. I'm going to show you right now. It's this guy here. Can you see that now? So that is my S pool. Okay, I'm going to walk you through how to be able to get that. And of course, this is the p-value associated with the test. Okay, this maybe what I'm going to do today. I think I'm actually going to walk you through the theoretical form of this material, because you know why? I need you to, I want you to understand the formula. Okay, I need you to understand the formula. Okay, when you understand the formula, you will not have any issue at all. Okay, I'm actually going to stop in the next 8 minutes, but I'm going to walk you through the formula that you need. Okay, if you want to figure out any test. So let me tell you something now. If you're doing randomized complete block design, okay, if you're doing randomized complete, if you're doing test of means, if you're doing test of mean, okay, in a multivariate setting, if you're doing test of mean, okay, you are comparing two populations, treatments, you understand, and you know where they are independent samples. So this is what you need to do. If you want to test hypothesis, this is what you need. Okay, this is what you need. Okay, what hypothesis are you testing right here? You are actually testing this, the quality of the vector means. Okay, so, and of course, this is going to be the confidence interval. Okay, if you want to find the formula of the confidence interval, so this is what you are actually going to use. This guy here. Okay, this is what you're going to use, and this is the Befferoni version. Okay, this is the Befferoni version. Okay, now another one, we're still on the comparing two populations, but this time around, what of in a situation where the population of variance covariance are not the same. Now, what we did, do you know why we use the pool? Why we actually use the idea of pool variance right here? Why do we need to use the idea of pool variance in this test? Is because we get an assumption. What was our assumption? Our assumption is that the two population variance covariance are the same, because we have assumption when you are comparing two groups in multivariate setting. Okay, if the assumption is that the two variance covariance are the same, if we have that assumption, of course, this is what we, if you actually want to test for the equality of means, this is what we're going to be doing. Okay, but in a situation where there's an assumption that the variance covariance are not the same, if the variance covariance are not the same, the variance covariance of the two populations, if they are not the same, then what I'm actually going to do is actually going to be different formula if I want to test for the equality of mean. Now, let me tell you right now, if I want to test for the equality of mean, now the formula that you need to do, your Otelin t-square is going to be this. This is the formula. the Hotelin T-squared is actually going to be this. Okay? That is the Hotelin T-squared. You know, what am I testing? I'm actually testing this hypothesis. If the Hotelin T-squared equal to this, then if I got this one, I'm going to use T-squared, you know, to multiply. You can see what I have right here. The test statistic is T-squared, okay? And of course, the T-squared is the one I got from here, okay? I'm actually going to compare the T-squared with the calculated value. And you know what? There's a V right here. And what is the V? This is the expression for V, okay? I need to first figure out this V, okay? I need to figure out this V. And when I figure out this V, I'm going to plug it in right here, okay? And I'm going to, you know, get a critical F and multiply by this. Then that is going to be the rejection region. So when T squared is greater than this, I'm actually going to reject the null hypothesis, okay? So never mind, never worry, you know, I'm still going to walk you through. What I'm trying to show you right now is just to show you the right formula, the formula we're going to use. Of course, in the exam, I'm actually going to allow you, you know, to write. You're going to have access to all your formula. But the only thing is that you should be able to know, you'll be able to figure out the right formula, okay, that you're actually going to use, okay? But I'm trying to point that to you right now, okay? Now, the last thing I'm going to talk about today is one-way analysis of variance. Of course, I've talked about two-way, I've talked about randomized complete block design. Now, but this is just the one-way version. Now, if you look at what I have here, is the univariate case. Of course, when you are dealing with one-way ANOVA univariate case, of course, you are aware of this model, okay? You are aware that, okay, we're actually going to have a model. This is the mean, this is the random component, and the mean can be broken down into this plus that. This is a treatment effect. It's just like the fertilizer that I talked about the other time at different levels, okay? Now, you don't need to worry about that. But you know what? We're actually going to have an ANOVA table, okay? We're going to have an ANOVA table. This is an ANOVA table for one-way analysis of variance. I think you guys are aware of that, okay? If I have treatment levels, the levels of treatment is G. The degree of freedom is going to be G minus 1. The other time, you know, I have 4 levels, and that will be 4 minus 1, okay? And it's going to be the number of experimental units. This is the sum of square, the source of variation. This is going to be sum of square treatment, sum of square error. This is total sum of square. So, of course, you guys are familiar with the table of analysis of variance. So this is the univariate version. If I want to consider a multivariate version, of course, I'm going to take you to the table. We're going to have, now take a look at, this is a multivariate version. So this is, instead of also have ANOVA, we're going to have MANOVA, okay? We're going to have the source of variation. This is treatment. This is error. This is total. We got degree of freedom, the G minus 1. The G is the levels of treatment. Then we have N minus G. We have N minus 1. Then under we're going to have sum of squared cross products, okay? And we're going to have, this is the formula. This is B. We're going to have within. And this guy here is going to be this plus this. And let me tell you something. This is going to be a matrix, okay? This is also going to be a matrix, okay? And when I add matrix to matrix, this is also going to be a matrix. Now look at what we're going to do. We need to find wiki lambda. Now, in the test of treatment, of course, we got the vector. What we are testing here is the vectors of treatment. As against testing univariate treatment, just a singular treatment, one unit of measurement in the univariate setting, okay? Now, since B here, I need to find, is a matrix, I need to find the determinant of that. I need to find the determinant, look at that. If you take a look at it, this is, because my test statistic is this. I need to find the determinant of W, I need to find the determinant of within, okay? And I need to find the determinant of total, okay? And don't forget, you need to first get this one. You get this one, you add this to this is a matrix. This is another matrix. You add this to this, that will give you this, and this is going to be another matrix. Then you find the determinant of that. That's what you have here. You find the determinant of this one. That's why. So the ratio of these two will give us the test statistic. That is lambda. Okay, and we're going to have a rejection region. Okay, that we're actually going to compare this with. Okay, so you know what? I think what I'm actually going to do next, I'm going to continue from here on Monday. But you know what? On Monday, what I'm going to do, I'm still going to do my arrows. And where I stop, I stop here. I attach a material, and that material, I'm actually going to walk you through how you can use R to do that on Monday. Where how you can do all this in R on Monday. But you know what? Let me tell you this. Apart from walking you through how to do that in R, I'm also going to walk you through how to do that manually. Let me show you this. I attach a material right here that you can practice. I'm going to, give me 1 second, attach a material that you can actually practice. Okay, so I'm actually going to, so you can be looking at that material before Monday. Can you guys see maneuver worksheet?
Yes.
Okay, now the maneuver that I just talked about right now, take a look at this. You have a question like this. I'm going to walk you through this on Monday, but you can be going through that before Monday. I've already attached it. In the univariate analysis of variance, you're going to have a treatment 1, treatment 2, treatment 3 like this, but you are not going to have a vector like this. What you're going to have just to be 6, 5, 8, 4, 7 here, 3, 1, 2, 2, 5, 3, 2. But this is the way multivariate ANOVA is going to be. It's going to appear like this. And when it appears like this, then we can actually ask you to compute the wiki lambda that I just showed you right now and construct the maneuver table. I'm going to walk you through this worksheet on Monday, how to do that, okay? So, and with the R, look at that. This is the solution right here. You can be looking at that solution before Monday, okay? It's already attached. Look at that. I've already set up, look at that. I've already got my B and my W, okay? I showed you the other time. Then I can find the determinant of that. Determinant of this divided by determinant. Look at that. Look at that. Can you see that now? So I'm actually going to walk you through this on Monday. Okay? So is there anyone who want to ask questions today before I go? Because by 12:30, I'm actually going to have my office hour. Is there anyone who want to ask questions before I
Yeah,
go?
Professor, could you postpone, like delay your or postpone your office hour maybe like 30 minutes later? I mean, start at 1. Because so we probably could have some time to have the lunch.
Oh, you're right. Okay. Okay, you know what is going to happen? I'm going to have an extended office hour because the office hour is for this class and another class that I'm teaching. So what I'm going to do, I'm going to have an extended office hour today. So you can go on lunch, okay? So you can join me by 1. I'm still going to be around. Does that make sense to you?
Yeah, sure. Thank you. Thank you so much.
Welcome. Is there anyone who also want to ask question? Okay, so I want to appreciate everyone for attending my lecture today. Like I said, I'm actually going to walk you through both the manual, what I reviewed today is just some formula, okay? And what I'm going to do, what I'm going to start with on Monday, I'm going to start with the worksheet material where I'm actually going to walk you through how you can set up maneuver table manually and how you can use R to do that. Okay, so that is what I'm going to do on Monday. Okay, so I'm going to have my office hour by 12:30, and it's actually going to be an extended office hour. Okay, so I want to say that I want to thank everyone for attending my lecture. Make sure you stay safe and see you on Monday, and have a good weekend.
Thank you.
You're welcome.
See you.
Okay.